Hello! In this video, we are going to prove the extreme value theorem, which says the following. Suppose f is a function from the closed interval a comma b to r, and f is continuous on a comma b. Then, f attains a maximum value and a minimum value on a comma b. Now, in this video, we're only going to prove that f attains a maximum value. So, in proving this theorem, we're going to use the concept of partitions of an interval. So if we consider our closed interval a comma b, well then a partition of a comma b is a collection of non-overlapping closed intervals whose union is a comma b. So this collection of closed intervals would be an example of a partition of a comma b. And we might label these closed intervals I1, I2, and so on. And we might label the endpoints of these intervals x0, x1, x2, and so on. So that's what a partition is. Now a tagged partition is when we select a point from each of these subintervals. And let's say that the points we select are these. Now the points that we select are what we call tags, and we might label the tags T1, T2, and so on. So that's what a tagged partition is. And the way we might symbolize a tagged partition is by a letter with a dot on top. And we denote the collection as a collection of ordered pairs. Each ordered pair consisting of the subinterval and the tag in that subinterval. So just like that. So now let's talk about what a gauge is. A gauge on the closed interval a comma b is a strictly positive function defined on a comma b. Right, so that's all a gauge is. For example, the function defined by delta of t equals t squared plus 1 for any element t in a comma b would be an example of a gauge on a comma b. Now, if we're given that delta is a gauge on a comma b and p is a tagged partition of a comma b, then we say that p is delta fine if the following is true. We say p is delta fine if each subinterval of the partition is a subset of this interval, which is an interval centered at the tag of the subinterval. So the way that you can visualize this is if we consider our subinterval II, we'll say it's right here. And let's say that the tag of our subinterval ti is located right here. Well then, this interval is an interval centered at ti, and its radius is delta of ti. Or in other words, its radius is the output value of when you send the tag ti into the gauge function. And so this interval might look something like this. And so the idea is, for the partition to be delta fine, we need each subinterval to be a subset of this interval centered at ti. So for example, for this partition to be delta fine, we need I1 to be a subset of this interval centered at T1. We need I2 to be a subset of this interval centered at T2. We need I3 to be a subset of this interval centered at T3, and so on, for each subinterval in the partition. Now, a fact that we've proven is if delta is any gauge function on a comma b, then there does in fact exist a partition of a comma b that is delta fine. So these are the ideas that we're going to be using to prove the extreme value theorem in this video. Okay, so now let's get into proving this theorem. Now, to start the proof, we're going to be using a fact that we have proven in regards to f being continuous on a comma b. Since f is continuous on a comma b, it follows that f is bounded on a comma b. And by the completeness property of the real numbers, that implies that the set of output values of f has a least upper bound. And we're going to let m be the least upper bound of the output values of f. So m is an upper bound of the output values of the function f, which means m is greater than or equal to every output value of the function f. So then, if we can show that m is itself an output value of the function f, that implies m is the maximum value for f. So our whole goal from here is to show that m is an output value of the function f. And to show that, we'll assume for a contradiction that m is not an output value of the function f. Now we know that m is greater than or equal to every output value of the function f. But what we're assuming here is that m is not equal to any output value of the function f. So putting those two together, we must have that m is strictly greater than every output value of the function f. Now, since f is continuous on a comma b, this means that f is continuous at every point in a comma b. So in particular, if we consider an arbitrary element t in a comma b, well then, f is continuous at t. And by definition of continuity, to say that f is continuous at t means the following. It means for every epsilon greater than 0, there exists a delta greater than 0, such that for all x in a comma b, if absolute value of x minus t is less than or equal to delta, then absolute value of f of x minus f of t is less than or equal to epsilon. Now, this definition is equivalent to if instead of weak inequalities, we have strict inequalities here. But for us, we're going to use weak inequalities. So since f is continuous at t, this means that this statement is true. And this statement works for every positive real number. So in particular, it must work for the positive real number m minus f of t over 2. So replacing epsilon with m minus f of t over 2, then there exists a delta greater than 0, such that for all x in a comma b, if absolute value of x minus t is less than or equal to delta, then absolute value of f of x minus f of t is less than or equal to m minus f of t over 2. And so what this shows is, we can take each element of a comma b and map it to a positive number which has this property. Right? We can map another element of a comma b to a positive number which has this property. We can take another element of a comma b, map it to a positive number which has this property. So in essence, we're taking each element t in a comma b and mapping it to a positive number delta of t, which has this property. So delta of t is a positive number defined for each element t in a comma b. And so delta is a gauge on a comma b. And since delta is a gauge on a comma b, well then, we know that there must exist a delta-affine partition of a comma b. And we'll call that partition P. And we'll say that the subintervals of this partition are symbolized by II, and the tags are symbolized by TI, from I equals 1 to n. Now, to reach a contradiction, the idea is to consider the following value. We consider the value m tilde, which is the maximum of f of t1 plus m over 2, f of t2 plus m over 2, f of t3 plus m over 2, and so on, all the way up to n. Now, it's clear that m tilde is less than n. The reason why is because since m tilde is the maximum element of this set, well then m tilde is an element of this set. So m tilde has this form. So we can say m tilde is equal to f of ti plus m over 2 for some integer I between 1 and m. But remember, every output value of the function f is less than m. So in particular, f of ti is less than m. Therefore, m must be greater than the average of these two numbers. And so this shows m tilde is less than n. But the claim is that we can show m tilde is an upper bound of the output values of f. If we can show that, well then, since m is the least upper bound of the output values of f, that implies m is less than or equal to m tilde. But that contradicts the fact that m tilde is less than n. So that's how we're going to reach a contradiction. We're going to show m tilde is an upper bound of the output values of f. And to prove that, we want to show for all x in a comma b, f of x is less than or equal to m tilde. If we prove this, then that will prove m tilde is an upper bound for the output values of f. So let's give ourselves an arbitrary element x in a comma b. Well then, since P partitions a comma b into a bunch of subintervals, we know that x belongs to one of these subintervals. So we can say x belongs to some subinterval II. But since P is delta fine, then II must be a subset of this set, which is centered at the tag Ti. And therefore, x lies between Ti minus delta of Ti and Ti plus delta of Ti. But then, by properties of absolute values, this means we have absolute value of x minus Ti is less than or equal to delta of Ti. And so this analysis shows that we can find a tag Ti such that absolute value of x minus Ti is less than or equal to delta of Ti. But now, let's go back to the definition of our gauge function. For each element t in a comma b, delta of t is a positive number which satisfies this statement. So, replacing t with ti, well then delta of ti is a positive number that satisfies this statement. And this statement works for every element of a comma b. So in particular, it must work for the element x. And we know that absolute value of x minus ti is less than or equal to delta of ti. That's what we have here. So we can conclude that absolute value of f of x minus f of ti is less than or equal to m minus f of ti over 2. But then, the thing to observe from this inequality is that we know f of x minus f of ti is less than or equal to its absolute value. So this implies f of x minus f of ti is less than or equal to m minus f of ti over 2. So adding f of ti to the other side, we get this, but then combining these two guys together, this is just m plus f of ti over 2, or otherwise just f of ti plus m over 2. So from this inequality, we can obtain that f of x is less than or equal to f of ti plus m over 2. But remember, m tilde is the maximum value of this form. So this value must be less than or equal to m tilde. And this shows f of x is less than or equal to m tilde. So what we have shown here is, if x is any element of a comma b, then f of x is less than or equal to m tilde. So we have proven precisely this statement. And that proves m tilde is an upper bound for the output values of f. But then, since m is the least upper bound for alpha values of f, then m must be less than or equal to m tilde. But that contradicts the fact that m tilde is less than m. Our assumption that m is not an output value of the function f led us to a contradiction. Therefore, m must be some output value of the function f. But remember, that was enough to say that m is the maximum value for f. Because we know that m is greater than or equal to every output value of the function f. But since m is itself an output value of the function f, well then m must be the maximum value for f. And so this completes the proof. And so yeah, that's pretty much it for this video.